Hello everyone. Today this class gets even sketchier as we teach class from the comfort of my house while I'm wearing pajamas. So tomorrow is going to be normally when class is Wednesday, and that is going to be very, very cold, and so classes are canceled. And so here we are. Let's get started. So, quiz first of all. Obviously, it's not going to count for anything, but take a look at this function. F of x equals w2 times maximum of 0 and w1 times x. And tell me what you think that could represent in the, as far as neural networks go. Alright, so pause if you haven't figured it out by now, but the answer is B. This can represent a two-layer neural network with a ReLU activation. As you can see, it has the max of 0 and the last activation. That clues us into the fact that it's ReLU. So, first, something neat to look at here. Found this on the IMTrust GitHub. This is an 11-line Python neural network from scratch. We have inputs, we have outputs. I don't know what the inputs and outputs represent, but we have them. And we have weights that are synapse 0 and synapse 1 there. We have a feed forward, and we have 60,000 epochs there, but we have a feed forward with our L1 and L2 lines there. We have our meat of our back propagation with our calculating error and calculating delta with our L2 and L1 deltas there. And we have our adjustment right at the end. We don't have a learning rate here, but that's fine. That just means our learning rate is 1. So, what activation function is this using? Just with a quick look over. Alright, the answer to that is, this is a sigmoid. You can see that with the 1 over 1 plus e to the negative x there in our L1 area. So, course logistics today. Our subject is Neural Networks 2, and we're going to be covering implementation libraries. So, a little tangent first on preprocessing. There's one type we're going to look at, and that is how do we represent our data with different classes. Of course, we need it to be numerical because that's what neural networks take, is numbers. But how can we best translate our categories into numbers? For this case, let's think of it as our category for our data. Let's use an example where we want to we have the favorite chips of somebody to eat. Everyone's favorite chips. We have, it could be Doritos, it could be Lay's, it could be Tostitos, whatever. Let's look at a naive approach to this. We just assign a number value. So for Doritos we have 1, for Lay's we have 2, for Tostitos we have 3. Another possible example, this is the MNIST dataset. It is a bunch of images, all 28 by 28 pixels, and they're all handwritten digits. They correspond to their labels, which are 0 through 9. And of course, we can just assign them the values that they represent. 0 is 0, 1 is 1, 2 is 2, etc. Problem is, we don't want the classifier to go in with information that isn't necessarily true. We don't want it to have intrinsic information about the data set based on the categories and what we define the categories as. So in this case, we might have a picture of a 1 and a picture of a 2 and a picture of a 9, and the picture of the 1 might be closer to the picture of the 9 in like what pixels are lit up. But the neural network might think that no, the 1 and the 2 have to be more similar because 1 and 2 are closer to each other than 9. Now this is kind of a weird example and not a great one, but and then a neural network will be able to get past this somewhat by itself, but it makes it a lot easier, and for larger data sets it can make it a lot better if we don't have a lot of intrinsic information coming in with the encoding, with the way we encode the categories. We don't want the neural network to make assumptions about the data based on our category labels or class labels. So how do we encode it without that? How do we ensure that it's not going to make assumptions based on our encoding? Well, we use one-hot encoding. One-hot encoding is basically, instead of representing the categorical data as a value, we represent it as a vector with length equal to the number of categories. Each category is assigned an index of the vector, and only one of those categories is going to be true, is going to have the 1. Everything else is going to be false. So basically, we split one attribute into n attributes, and while the attributes used to be like an integer, like in our naive one we could have it as an integer representation, we're basically now doing this as a Boolean or a binary representation, 0 or 1. We have 0. We turn the question of what number is this? Is this into, is this a 5? Is this a 4? Is this a 3? If we're talking about the chips one we were messing with before, instead of saying is this a Doritos? Is this Lay's? Is this, what is this? It's just, is this Doritos? 0. Is this Lay's? 0. Is this Tostitos? 1. And that, of course, would represent someone who preferred Tostitos to Doritos and Lay's. And here we have more examples. The 5th index, there is one representing a 5. The 0th index is 0, representing a 0, and so on. Now, tangent over, let's get to neural networks. So, what questions do we have to answer before we can actually implement something? Well, we need an activation functions, that's for sure. We also need functions that let us predict and learn from our neural networks. As far as data goes, what do we have to store and how are we going to store it? Overall, how do we make this entire process efficient? Because if we don't have efficient neural networks, these could take days or hours or years to run. If we were to do this randomly, like randomly assign weights every time, or randomly assign weights without doing some sort of backpropagation, this thing could be lifetime of the universe long to run. So we need to do this in a way where we're training and using the neural network is efficient. Start with the activation functions. This is really simple. Just plop them down into the code, convert them into Python, you're good to go. Don't forget the derivative though. We still also have to have the derivative function defined as well. It's also important to remember that if you have a derivative activation that calls the original activation, it might be useful depending on how you implement it, but at the same time, if you ran that feed forward before in the backpropagation, if you started with a feed forward and you take that same data and then you run it through for the backpropagation, you won't have to do that f equals tan hx. You won't have to call the original one because it's already gone through tan h, and in that case we could just have it be f equals x, or just run 1 minus x times x. And again, that's the tan h activation. We won't be using that much, but we have ReLU above it, and we will reuse ReLU occasionally. Also, a quick note, the ReLU at 0 is a weird thing. In this case, we just have it act as 0, but one of the problems with ReLU is at 0 it doesn't have a derivative, but we approximate here, and in this case we're going to say the derivative is approximately 0 at that point. So, what do we store? Well, we need to store the weights, and that's about it. Everything else is going to be structural. How many neurons we have, how many layers we have, what activations they use. The only thing that is going to be changing during runtime and needs to be stored in memory is going to be the weights. But how do we do that efficiently? Well, we can store them as a matrix, and that way we can use matrix operations to perform a lot of our neural network operations. For example, if we want to multiply the inputs by the weights and then sum all of that, we can just use dot product. And of course, a really easy way to represent that in actual Python code is NumPy arrays. They'll handle a lot of that. In this case, beneath we have our weights, W1 and W2. Those are for different layers, layer 1, layer 2. And we initialize them with random values, and we make sure that the sizes of these layers are input size by, we have our two-dimensional matrix there, input size by hidden layer 1 size, and hidden layer 1 size by output size. So we have one weight for every input size, or for every input neuron and hidden neuron combination, because again we're working with a densely connected situation here. And we have, for the next layer, a weight for every single hidden layer output neuron interaction. So prediction and learning. We want to make these functions modular because a lot of the operations are done inside of each other. So, for example, forward pass, that's going to be used in a lot of the other functions here. We want to have a forward pass function that just pushes the information forward through our network, does our multiplications, our sums, our activations, and every single layer, it's going to have another output. So instead of just outputting the overall network output at the end, it's going to output the output from every single layer one at a time. We also have backpropagation. We can run the backpropagation algorithm through once and do a forward pass and then actually run our algorithm. So of course that is going to make use of our forward pass function as well. We can have another function, learn, that's just going to run several backpropagation cycles, also known as epochs. And yeah, it's going to be our main learning function that we call when we want to have our neural network fit to some data. And of course a prediction function that's just going to do a forward pass and only return that last output vector. The only things the programmer would be touching really are predict and learn. Backpropagation is just going to be something used in the learn function, and forward pass is going to be used in backpropagation as well as in predict. So, TensorFlow. Let's say we want to write a big neural network, or any neural network really, and we don't want to have to worry about writing all of our own activation functions, all of our own optimizations with backpropagation. We don't want to have to worry about all that every single time, writing a whole neural network from scratch. So we use a library, in this case TensorFlow. Now, what is TensorFlow really? Well, let's look at the definitions of the words that make it up. We have a tensor, which is a generalization of vectors and matrices to potentially higher dimensions. This is going to be the simple data structure we use to store information. And flow, the action or fact of moving along in a steady continuous stream. So what TensorFlow is doing is it is flowing tensors through something, specifically a graph, as we'll see later. Oops, there we are. So TensorFlow overall is a numerical computation machine learning library. It can do more than machine learning, but mostly we'll be using it for that, and most people do use it just for that. And it lets you build graphs of operations and flow data tensors through them to get output tensors. We can use these graphs as neural networks, and we can use the tensors as inputs, outputs, and weights. So let's have this little data flow graph here. We have two inputs, x and y. We have a constant 12, and we are going to have two operations. We multiply, and then we add, and that is going to go into the tensor that we call C. To those of you who've taken compilers before, this might look a lot like an abstract syntax tree, and that's because it basically is. You can definitely think of TensorFlow as being its own language. It's one where we have to explicitly encode its abstract syntax trees. We can't write it out on its own, but it's a language nonetheless, and niche but powerful. Important parts of TensorFlow. We have the graphs. That is going to be TensorFlow's implementation of our data flow graph. It's made of operations and tensors, and the default one is going to be accessed by get default graph. Now, the reason we have that default one is because TensorFlow has a weird way of, when you create an operation or a tensor, it'll automatically add it to the graph instead of having us explicitly add it. So get default graph is just going to be the graph it's adding to. You can have it set up so you would do it with your own graphs, but for right now we can just look at it as messing with our default graph. We have TF operations. That's going to be the nodes. Those are going to consume and produce tensors and run different calculations on them. Tensors, of course, are main data structure we're using to hold data. Most functions in TensorFlow are going to return tensors of some sort or another. And finally, we have sessions. So if our graph in TensorFlow is like our code when we're programming, then our session is going to be like the running process of that code, an instance of that code. Best way of creating one is just using the with syntax in Python with tf session as ses, and you can use the ses.run function to run portions of our graph and get output from them. And also worth noting, the tensors, except for global ones, all the non-global tensors are only going to persist within our session. The data in them is not going to last when we aren't running the session. And that can be seen here. We have two constants we create. One of them we specify the data type and one we don't. It's able to figure out on its own. And we also have an output tensor we call total, which is just the addition of A and B. When we print all of our tensors, including our output one, we get these data structures, but we don't actually have our answer, our 7 that we're looking for, because this is just the structure of the graph. This is not at all the calculation. here's a little graphical representation of our TensorFlow setup here. I did goof a little on the bottom one there. That's supposed to be b equals 4, but regardless. So let's run a simple example. It's going to be just like our other one with a and b in total. However, this time we are creating our session and we are running it. We are specifically running total, and it will start at that node and recurse back into the graph, running everything that needs to be run in the graph to reach that node, and eventually output 7. Ses.run will give the output of that tensor, that total tensor, and that will of course be 7 when we add 3 and 4 together. So yeah, when we do ses.run, we're passing the tensor that we want it to output. We can also output to multiple tensors if we use an output dictionary. Dictionaries in Python are super great. Definitely, if you don't know them, learn how to use them because they're the most useful thing ever. But in this case, we give it this special little dictionary with our A and B and total, and it's going to return a dictionary just the same as the one we gave it, but except with the tensors switched with their values that we've calculated during our session. Now, how do we do input-output stuff? We had constants, but how do we have real input to our graphs? Well, we can use tf.placeholders. These are special tensors that are just holding the position. It's a variable basically, and we can use it as a name and stuff, but it's not going to actually hold any information until we run our session and feed it that information. Same setup as before, except instead we've named total z. We have z equals x plus y. And when we run our session here, we run z, but we also give it a feed dictionary, and that's going to have the values we're setting for our placeholders. Notably, we can definitely feed in just single values, 3 and 4.5 for example, and that adds up to 7.5, but we can also put in vectors or matrices or whatever sort of data we want to do it with. In this case, we add in 2 lists, and it is able to add those lists together by element-wise, 1 and 2, 4 and 3, and we get our 3, 7 vector there. So let's make this one we saw before. We have our 2 placeholders, x and y. Those will be our inputs, and we also have a, which is going to be our constant of 12. We call that multiplication output 1, and we set that to be x times a. And we also have c, which is going to end up being that output 1 plus y. We run the session, we supply in for x 10 and y 5, and set that as our feed dictionary, and we're off. And of course, we just end up getting 125 total there. This class is not going to be specific to TensorFlow a lot. We talk about it a little, and we talked about it a bit here, but mainly we're going to be using Keras for stuff, and TensorFlow is good to know, but we're not going to cover much more of it from here. A few bits that are useful though. TensorFlow has loss functions in there already made. Softmax, cross entropy, mean squared error, both very useful. It has already built for fully connected layers for our neural networks. It has a reshape function, so we can reshape the dimensions of our vector. It has variables, which is a special tensor that can exist outside of our session. And we also have our atom optimizer, which is basically the same as our gradient descent that we worked on last class. It's just an extension of gradient descent, and it's going to optimize our weights for us. One moment now, I need to plug in my phone because it's decided that it wants to die. I apologize again for this being a sketchy version of lecture, but makes it so we don't have to waste a day of the week or a whole week. That plugged in-ish now? Yeah, that's plugged in-ish. Alrighty. So, quick pros and cons of TensorFlow. From a novice perspective, there aren't many cons to TensorFlow. It is a little low level for us, where it's not the perfect level of abstraction we'd want, where we can do things more easily. And it also can be difficult to learn. On the upside, though, the data flow graphs are a very efficient way, and a very dynamic way of modeling neural networks. They can also be parallelized or run on GPUs very easily. And TensorFlow overall is extremely widely used in the industry. TensorFlow is much easier to use than just from scratch neural networks. It has a lot of extras built in, so we can, like the activation functions we saw before, like the many loss functions. And TensorFlow also has Keras built into it, which we'll see a little bit more about later. And it's open source, which is always nice. Alright, so Keras. Keras is the high-level neural nets library that we're going to be using, and it's built atop TensorFlow, CNTK, and Theano. That means that if you know Keras, you can use it in a TensorFlow, CNTK, or Theano environment, because it's just higher-level APIs for all of those three libraries. It's also the official API of TensorFlow, which means it's built into the TensorFlow library, and if you have TensorFlow, you also have a version of Keras. You can access it just through TensorFlow with tf.keras or whatever, and you can use it just as easily as the low-level API of TensorFlow. Keras is mostly what we'll be using in lab. Specifically the version of Keras coming with TensorFlow. For that matter, you can in labs. For most of the time in labs, we'll give you the option to use TensorFlow or Keras, but usually it's easier just to use Keras, and you can do a lot more with it a lot more quickly. So for Keras, we're just going to learn by doing. Let's build a one-layer neural net. And we just want it to have an input shape and an output shape as defined by those constants. So first we'll have a function that builds the neural net. It's just the structure. It's not going to train it or run anything on it. So we create a model. Sequential model is just a set of operations, and it's going to go one at a time through that sequence. Next, we're going to create a loss function. For this one, we'll just use categorical cross entropy, and we'll create an optimizer. Again, we're using that same TensorFlow atom optimizer we talked about before. Now we're going to create and add to our model a new layer. Just a layer of neurons all at once there, and we're going to give them the activation function TF and then softmax, which is our softmax activation. We're also going to specify our out shape and input shape there. And then we compile our model, because that's all we need. We just have that one layer, and our model is just going to be our optimizer and our loss added into it. It's the sequential stuff we've added to it, and we're specifying what optimizer and what loss function we're adding. And then once it's compiled and it's finalized and everything, we can return it just as that model. So if we want to train our neural network, we need the model, we need our X and Y, our data describing our records and our labels for our records, and we're going to need the number of epochs we want to run it. For this I picked 6. For image processing you're going to need a lot more. I think the amount you're going to be using in the lab is, for the TensorFlow ones, is like 100,000 or something like that. Notice that all we have to do is call model.fit. We don't need to worry about backpropagation or feedforward or any of that. It'll handle that itself. Again, for running, all we need is the model and our X data to do our predictions. We just model.predict and we get our predictions out. And it's just such a simple little function call we can do. And just those 3 functions right there, we have a perfectly working, perfectly easily trained and running network. So Keras is really easy to use, but remember, it's just a higher level API of TensorFlow. All the same data flow graphs and stuff are happening under the hood. It's just a little more programmer friendly. And TensorFlow is really just an easy way to architect our data flow graphs and a set of different functions and calls that we can use that make our objects and stuff that let us create these data flow graphs in more complex ways. And to dive one level further again, all these libraries, TensorFlow and Keras, they're not doing things under the hood any differently than we would if we were doing it from scratch. We might have slightly more complex algorithms, like using Atom instead of using standard gradient descent. And we might have more options for activations or loss functions or whatever, but all of this is still the same thing. We're still using the same steps to create a neural network. The only difference is we can do it a lot cleaner and a lot more easily and often a lot more efficiently. So to close things out for the day, here's a quick little neural network I made myself here. 7 lines only, MNIST digit recognition classifier. So can you see it on the camera there? Let's zoom in a little. Sort of. Well, you can look at the slides if you want to. We import our data from the little handy Keras utility that lets us import MNIST. We do a little bit of pre-processing, just setting things from the 0-1 range, or from the 0 to 255 range to the 0 to 1 range with our division there. We create our model, which is going to be a sequential and is going to have those densely packed layers in there, as well as a flattening layer to just get everything from our 28 by 28 pixel layout to our 784, I think. 28 squared, yeah, that's 28 squared layout, just having all of our pixels flattened. And then we're going to compile our model. We have our optimizer, which is Atom, our loss function, which is sparse categorical cross entropy, and we are going to add a metric in there. It'll track accuracy for us. Finally, we use model.fit to train our network. We give it 5 epochs there, which is usually not enough, but it works fine here, it looks like. And we print our loss and our accuracy on our test data. And we end up with a 97% accuracy, which is not bad for something written in 7 lines. So that's it for today. We have our links for TensorFlow. Definitely look at some of those if you want to know a little bit more about them. I think there's also some Keras stuff in there, but most of what we'll be using is Keras. And oh yeah, the project. So the project will be out the 30th, whether that is today, in which case I updated it tomorrow, or it is, yeah. Right now it's Tuesday. I might upload it tomorrow, Wednesday, and Wednesday is when the project will be out. It is going to be basic classification. You are going to be making your own custom neural network as well as creating one in either TensorFlow or Keras. You'll be doing some pipeline stuff, and we'll see how well you can classify MNIST. Yep, that's it for today. See you next week.